Hey guys, it's Miss Manili, and I'm going to give you a quick tutorial on the very last section of Chapter 6. In Chapter 6, we've been talking about all sorts of random variables, and since the exam, we've been talking about the binomial distribution. There are 4 criteria, which basically mean that there's a fixed number of trials, there's success and failure, probability of success is constant for each trial, and the trials are independent. We've also talked about the circumstances in which a normal distribution can be used to model a binomial. And today we're going to talk about another type of random variable that's called geometric. The geometric random variable is actually very similar to the binomial. So we'll talk about the conditions, we'll find some probabilities, and then we'll even talk about expected value for the geometric. So let's talk about the geometric setting. When we were talking about the binomial setting, we said the number of trials is fixed. And the random variable itself counts the number of successes in those n trials. So if there were n trials, then the possible values for x could be 0 if there weren't any successes, or 1, or 2, or 3, and so forth until we get to n, which is the number of trials. Geometric is slightly different. In this situation, our goal is to repeat chance behavior until a success occurs. These situations are called geometric settings. So a geometric setting arises when we perform independent trials, so we still have that requirement of independence. It's the same chance process, and we record the number of trials it takes to get one success. So instead of counting the number of successes in n trials, we're looking to see how long it takes to get a success. On each trial, the probability of success must be the same. So that condition is the same as it was with the binomial. All right, so I put a star next to this because I think that this would be a good idea to put on your study guide. In the geometric setting, we define the random variable, this time I'm going to call it y, to be the number of trials needed to get the first success. Then y is called a geometric random variable, and the distribution of y is called the geometric distribution. And there are actually 3 conditions for the geometric setting, and number 4 is just how the variable is defined. So the first one, again, is observations fall into 2 categories, either success or failure. The probability of success, same as before, we're going to call it P, and it must be the same for each observation. The observations must all be independent. So the 4th condition for a binomial was that there were a fixed number of outcomes. The geometric setting does not have that condition. Instead, the random variable is defined as the number of trials it takes to get one success. So no matter what, every outcome includes one success because we're gonna keep performing trials until we get one. So unlike the binomial distribution where we could have 0 successes, in the geometric setting, the lowest value our random variable can take on is 1. But it's also infinite because it can keep going. I can look to see how, the probability of getting my first success on the 10th trial, on the 100th trial, on the 1000th trial. So there is no end to the values that it can take. The notation that we use now is just going to be that x is our random variable, and it's distributed geometrically. And you could also just use a capital G instead of writing geo. But we only have one parameter now, and that's the probability of success. Since we don't have a fixed number of trials, we don't need to include that. So it's just geometric, and then the only thing you really need is the probability of success. All right, so we've got a couple examples here, problems 1 and 2. And what I'd like you to do is think about the information that we just said and the different settings that we have and determine whether or not the distribution would be considered geometric. So I'd like you to go ahead and pause the video for a minute and go ahead and answer these questions. Okay. So if we look at the first one, it says an experiment consists of tossing a single die until a 3 is rolled. So again, with a die, a success in this case would be a 3. A failure would be anything else but a 3. The probability of success, since there's 6 sides, would be 1/6. We can assume when we toss a die that our trials are independent. So this actually does, sorry, that's really written small. This does qualify as a geometric distribution because we're counting the number of tosses it takes to get a 3. So I would say that x is distributed as a geometric random variable, and the probability of success, that should say 1/6. I'm sorry, I must have typed a 3 in there, but this should say 1/6 since there's a 1/6 chance that we'll roll a 3. In the second one, it says an experiment consists of repeatedly drawing cards without replacement from a deck of 52 cards until an ace is drawn. So that sounds good. It sounds like geometric. In this case, our success would be drawing an ace. The probability of success then would be 1/13 because there are 4 aces and 52 cards. So 1/13 would be our probability of success. However, if we're not putting the cards back, if we're not replacing them, our population isn't large enough for the probabilities to remain pretty constant. So because we don't have independence, this is not a geometric distribution. And finally, in a basketball, we're going to attempt a three-point shot until a basket is made. And again, this sounds geometric, but we got to think about, you know, the information that we need. So a success in this case would be making the three-point shot. The problem is we don't know the probability of success. That doesn't mean that it's not geometric. It just means that we wouldn't be able to actually calculate any probabilities. So our probability of success is unknown. A failure in this case would mean not making a shot. If we assume that all the shots are independent and the probability of success, the probability of making a three-point shot, is constant, then we would have a geometric distribution. X would be distributed geometrically, but we wouldn't know the value of P. But it would still be geometric. We just wouldn't be able to calculate any probabilities. If we take a look at the second problem, this has to do with a Monopoly game. One way to get out of jail is to roll doubles. Suppose that this was the only way a player could get out of jail. Let the random variable of interest be y equals the number of attempts it takes to roll doubles one time. So we want to describe the distribution of y using proper notation. I'm actually going to scoot over. All right, so in this case, we have a success, meaning rolling doubles. The probability of success, sorry, this is really tiny. If you think about all of our outcomes, we can get a 1-1, a 2-2, 3-3, and so forth. And if you think about tossing 2 die, remember there's 6 outcomes on the first die, 6 outcomes on the second die. So if we multiply those together, I know there's 36 possible outcomes. If 6 of those outcomes constitute a success, then my probability of success would be 1/6. If I'm tossing die, I also have independence. And since I'm looking for the number of tosses it takes to get a double, then this is a geometric distribution because the tosses are independent. So I'd say y is distributed geometrically with a probability of success of 1/6. In the next one, it says, how could you determine the probability that it takes 3 turns to roll doubles? Well, that means I've got a failure on the first roll, and a failure on the second roll, and a failure on, and a success on the third roll. Well, if my trials are independent, then I can just multiply my probability of failure times the probability of failure times the probability of success. Well, if success has a probability of 1/6, then that means failure has a probability of 5/6. So that's essentially 5/6 to the second power times 1/6. The geometric probabilities are really easy because you don't have to worry about the number of ways to get 3 because there is only one way. The success occurs on the very last trial. There's only one way that can happen. So it's otherwise, the formula is essentially the same as the binomial. We have the number of successes raised, we have the probability of success raised to the number of successes times the probability of failure raised to the number of failures, but in any one of these cases, we're only going to have one failure. So the probability is a lot easier to calculate. So if I multiply that out, I get 25 over 216, or about 11.5%. Take a look at the next question. This time, we're asked, how could you determine the probability that it takes more than 3 turns to roll doubles? So more than 3 would mean that we're talking about x is greater than 3. And if I think about what that means, it means that x could be 4, or x could be 5, or x could be 6, or x could be 7, and so forth. There's an infinite number of possibilities, and I can't add them all together. Well, think about what we did with the binomial distribution. If I take the complement of this event, then at 1 minus the probability that x is less than or equal to 3. And that is finite, because then I just need to find the probability that x is 1, plus the probability that x equals 2, plus the probability that x equals 3, and then subtract that sum from 1, and that'll give me the complement of this event. And so if I do that, obviously it's a nuisance to add all those probabilities together, so I'm going to jump right into showing you how to do this on the calculator. It's essentially the same thing we did with binomials. The geometric is really simple. So this is the geometric probability formula. Anytime I'm looking for the probability that the geometric random variable equals anything, so let's say I'm talking about k, so the first success occurs on the kth trial, then I'm taking my probability of failure and raising it to the number of failures, which is always going to be k minus 1, times the probability of success. And I believe when I was saying this earlier, whoops, here we go, that I said this wrong. When we were looking at the probability that y equals 3, I had 2 failures. So we'd have the probability of failure raised to the second power. We're always going to have 1 success. I think I might have said that backwards, so I apologize if I confused anybody. All right, so we're always going to have the probability of failure raised to the number of failures, which is essentially always going to be 1 less than the k value. And then we'll always have just 1 success, and so that would be p. So on the TI-84, we're going to use essentially the same commands that we did with the binomial, except we're going to choose the geometric option. So if I'm looking for the probability that y equals a number, I'll use the command geometric PDF, and remember we always enter our parameter in first. There's only one, and that's my p-value, and then k is my boundary. That would be my number of trials. For cumulative probabilities, it's the same as before. Cumulative means at or below. So if I'm trying to find the probability that y is less than or equal to k, I'd use the geometric CDF. Again, I'd put my p-value in first, and then my upper limit, which is k. If I was trying to figure out what would happen if I had the probability that y is greater than k, then I would just take the complement of that like we did with the binomial. So let's take a look at some more examples. I think there are 2 more. And what I'd like you to do is go ahead and pause the video again, and actually maybe there's just one this time. Pause the video and go ahead and answer this question. Okay, so if I take a look at number 3, we're talking about a basketball player making 80% of her free throws. We put her on the free throw line and ask her to shoot free throws until she misses one. Let X represent the number of free throws the player takes until she misses. So what assumption do you need to make in order to apply the geometric model? With this assumption, we need to verify that X is geometric, and then what action constitutes a success in this context. So in order for us to assume, the assumption that they're talking about in order for this to be geometric is that her shots have to be independent of the other. We also need to assume that her probability of success remains constant. If those are true, then success in this case is going to mean missing a basket. And so P would equal 0.2. So be really careful of how the probability is defined and how the random variable is defined, because you want to make sure you're being consistent. If a success means missing the basket, then the probability of missing the basket is going to be the complement of 80%, which is 20%. And then this is the notation that I would use to describe the random variable X. In the next question, we're going ahead and looking at the probability. So it says, what's the probability that the player will miss a basket for the first time on the 6th shot? So we're looking for the probability that X equals 6. And so if I think about it, that must have meant that she got 5 makes and 1 miss. So if I'm looking at the makes, that's going to be the probability of making the basket, which is 0.8 to the 5th power, times the probability of missing, which in this case is the success. And if I multiply that out, oops, let me actually pull up my calculator. So if I'm going to do this on the TI, this is an old version, sorry, I'm at home. So if I want to find the probability that X equals 6, I'm going to go to my distribution menu. The geometric distribution is at the very end. So actually, if you press the up arrow, it'll be the faster way to get to it. Since this is an equals, I want to use the PDF option. Now, if you have one of the newer calculators, I believe it does prompt you the order that you need to type. But just like with a binomial, we enter our parameter first. In this case, the probability of success is 0.2. And then I'm going to put a comma. If you have one of the newer ones, it gives you the prompt. I'm looking for 6 trials to get my first success. And so that's all I need to type in. And my probability would be 0.0655. If I look at the next question, it says, what is the probability that it will take at most 6 shots for her to miss for the first time? All right, well, at most 6 shots means that it was 6 or less. So if I go back to my calculator, this time I'm going to do a geometric CDF. So again, if I do second distribution and go up, the very last option on my calculator is geometric CDF. And again, we want to enter the probability first, which is 0.2. And my upper bound, which is 6 in this case. And so we get 0.7379, and that would be the probability in letter C. All right. The next thing we're going to talk about is the mean of a geometric random variable. With a binomial random variable, we said that the mean was n times p. With a geometric, it's just the reciprocal of p, or 1 over p. This formula is actually not on your AP exam. It's not on the formula sheet, so this would be something to kind of keep in mind. In terms of the standard deviation, because the random variable is infinite, it's much more difficult to compute the standard deviation, and that's not something that we cover in this course. So the only thing you'd be responsible for is knowing how to calculate the mean of a geometric random variable, which is just 1 over p. So you have 2 more examples that are left, 4 and 5. I'd like you to go ahead and pause the video again and go ahead and complete these 2 questions, and then I'll show you the answers in a few minutes. Your review tonight, or the homework tonight, is going to be the review of section 6.3. As a study guide, or to help you study, I would make sure that you complete the study guide that I gave you the first day of the semester, just to make sure you have all your formulas and all the really important notes that you need. There are a couple extra practice problems on the back that you can do as well. Our test will be Thursday and Friday this week. So I know we've had kind of a short week, but we need to keep moving because we need to get into inference, which is our next unit. So go ahead and press pause, and I'll come back and give you the answers to 4 and 5 in just a minute. Okay, I'm just going to run through the answers for number 4 and 5. I know it's kind of small. In number 4, you're given a jar with a lot of marbles in it. In fact, you have 35 marbles, 20 are red, 10 are blue, 5 are white. The experiment consists of selecting a marble without looking, noting the color, and then putting it back in the jar. We're interested in the number of marbles you would have to draw in order to be sure you have a red marble. This is going to be a geometric distribution. We would define the success as being a red marble. The probability of success would be 20 out of 35, which is 4/7. Since we're replacing the marbles after we draw them, the trials are independent, and this is a geometric distribution with a probability of success of 4/7. And so if you take a look at the probabilities, in letter B, we're trying to find the probability that x equals 2. That's almost 24, almost 25%. Letter C, we're looking at the probability of drawing a red marble by the second draw. That means that x would be less than or equal to 2, and that's 81.63%. Letter D, we're calculating the probability that it would take no more than 2 draws. I'm sorry, I said that totally wrong. That it would take more than 2 draws to get the red marble. So we're looking at the probability that x is greater than 2. And again, it's going to be easier if we just flip it around and look at the complement, 1 minus the probability that x is less than or equal to 2. And you should get 18.4%. The mean of our distribution, the mean the expected number of marbles you'd have to draw in order to get a red, is just 1 over the probability. Another way of thinking about it is just taking the reciprocal of the probability, and so that would be 1.75. And finally, the last question, Carla makes random guesses on a multiple choice test that have 5 choices for each question. We want to know how many questions Carla answers until she gets one correct. So a success in this case would be getting a correct response. Since x represents the number of questions answered until we get one correct, as long as we assume that the questions are independent and her probability of success, which in this case would be 20%, since there are 5 answer choices and only 1 is correct, this would be a geometric distribution with a probability of success of 0.2. Letter B is just looking for the probability that x equals 5. That's pretty straightforward. You're going to do the geometric PDF. In letter C, if we're looking for the probability that it takes more than 4, that's x is greater than 4, you have to work with respect to the complement, which is 1 minus the probability that x is less than or equal to 4. And then finally, the mean of the distribution is going to be 1 divided by 0.2, which turns out to be 5 questions. So I think you can see that the geometric distribution is very simple compared to the binomial. The important thing is that you are able to distinguish between the two variables. So just remember, just as we're wrapping up, the conditions for a binomial distribution, we've got success and failure. The probability of success remains constant for each trial. There are a fixed number of trials, and the trials are independent. For the probabilities, if you're ever asked to find the probability that x equals a value, you would choose the binomial PDF. If you're ever looking at the probability that x is less than or equal to, you can use the binomial CDF. If the probability is more than or greater than or equal to, then you have to rewrite it in terms of a less than or equal to. To calculate the mean of a binomial, that's just n times p. The standard deviation is going to be the square root of n times p times 1 minus p. And you do need to be able to interpret those values in context, so don't forget to put your units. You'll need to be able to use a normal approximation to the binomial by calculate those probabilities. And remember, we said that as long as the number of successes and the number of failures in your trials are greater than 10, then you can use a normal approximation. It's not just having a high n value or a p-value that's close to 0.5. It's the combination of, or the product of those two values. And if they are both over 10, then you can use a normal distribution using the mean and standard deviation of the binomial random variable. And the only reason that we ever really did that is because back in the day, there would be errors on the calculator if you tried to calculate some binomial probabilities. Like if there were too many successes or too many trials, you'd get that error overflow message. So we had to have a different method of calculating those probabilities. And then finally, we talked today about calculating the geometric probabilities. Again, the formula is so much easier. You don't even, I mean, if you're just finding the probability that x equals something, it's easy enough to do using your calculator than using the geometric PDF command on your calculator. So anyway, what I'd like you to do is go ahead and get started on the review guide. I will post the answers to the review guide on Blackboard so you can study. Obviously, you can come in for help. Wednesday we have advisory, but you're more than welcome to come in Thursday or Friday if you need help.